Okay, so hello everybody. Hope that you're ready for more. Up next, we're having Shady Adib. He's a research associate at the Africa Center for Digital Transformation. He will show us how physics informed ML and also generative AI and digital twins are transforming the way we monitor and maintain an infrastructure in real time. The stage is yours, Shadi. You can go ahead and tell me.
Thanks, Yusuf. Good afternoon, everyone. So I'm truly happy to welcome you to this technical tutorial session at DSC MENA 2025. So my name is Shady Adib, and today we were going to go to take a deep look at a subject where it's set intersection between civil engineering, artificial intelligence, and real-time monitoring technologies, which is a digital twin. So, but now just not digital twin in their traditional or conventional sense. We will explore how to advance them in integrating cutting-edge tools like physics for machine learning, or like generative AI and dynamic diffusion models. So my personal hope is that by end of this session, you will have not only a clear understanding about the theoretical background of digital twin, but also the practical tool and insight to begin applying these methods in your own research or industry. So regarding to the tutorial agenda, so we follow a structured journey. So we will start by building a strong foundation on what digital twin and why they are important in context of structural health monitoring or in civil engineering in a broad way. Then we will start describing and introducing the different techniques or different technology, emerging technology, which aiming to advance the digital twin, like physics informed machine learning, which is an amazing method that fuse mathematical modeling with machine learning or with the data extraction or understanding the data or learning from data. Following that, we will look at the Gen AI and how it can simulate failure conditions that are hard to capture in the real world, how the Gen AI can generate scientific data, which can provide us with a huge amount of data coming from unexpected scenarios, which we couldn't get in real time or in real applications. And then we were going to have a short break, and then we were going to explore the dynamic diffusion model, which is a probabilistic tool for detecting anomalies in a complex system. So we will then discuss the integration of these technologies with digital twin and how this will going to affect on the way we are monitoring the structures, particularly advancing the old way of monitoring systems we used to use as a civil engineer. Finally, we will walk through some practical software which currently we're using as a civil engineer, or the civil engineer used these softwares, which has digital twin capabilities integrated with our physical understanding as a civil engineer. So a little bit about me. So my name is Shady Adib, as I said. I have just finished my PhD at Newcastle University, focusing on developing digital twin for real-time structural health monitoring. So we're trying to develop a hybrid digital twin combining physics-based model and deep learning for real-time structural damage identification and prediction. Currently, I'm looking for advancing the digital twin or the developed framework through self-generating and hierarchical digital twin, enhanced by generative AI, dynamic diffusion model. I'm looking for as well for Internet of Everything, which we are aiming to integrate the human insight into the digital twin cycle. And then we are working on get use, as I said, of generative AI to create synthetic data, which help to enhance the efficiency of the developed hybrid model. So before my PhD, I completed my master in Lithuania, focusing on structural analysis of high-strength steel cold form tubular section. And before that, I completed my bachelor in my home country at German University. Okay, before we think about digital twin, just a quick poll here before we introducing this. Just wanted to see if anyone know about digital twin. So, right, so it's, I'm just trying to put the poll, just give me. Right, okay. Can everyone see the poll? Okay, yeah. Just 2 minutes and then we will continue and then we get answers. Okay, it's 50-50 now. Okay. No more answers. Right. So for those who don't know about digital twin, so digital twin is more than a digital model. It's a dynamic real-time reflection of the physical asset, physical process, physical system, physical performance, or a physical product. So a digital twin continuously receives this data and update a virtual model that mirrors the physical state of like a bridge or like a machine or like a motor or like the whole vehicle, for example. This is not just a simulation you run once. It's like a persistent system that learn and evolve over the time. Digital twin are used in aerospace, civil engineering, manufacturing.
Sorry for interruption. Yeah, you can.
Sorry.
Everybody can access the link on the chat. We just shared the PDF on the chat. Okay.
Thanks, Yusuf. Thanks so much.
Best of luck.
Right. So on the chat, you can see the link for the PDF guide for today's tutorial. So when we start the practical session with coding, you can, if you want to try it while I'm trying this with you, that's absolutely fine. You can do that. You can just copy paste the code in the PDF guide and try to run the code with us and see how it works with the while we are trying to run it. Okay, let's continue. So as I said, digital twin is used for different sectors, for different perspective. But the main question here is, I'm always saying, what do you want from digital twin? So when you introduce a problem, when you introduce an issue, what do you think digital twin can achieve in order to solve your problem? So they allow us to anticipate problems, simulate what-if scenarios, and make this data-driven decision in real time. The major shift here is from reactive maintenance, from my perspective as a civil engineer, is a transition from reactive maintenance to predictive and even prospective maintenance. So the main idea here is not just to real-time simulate or to get a feedback or to get an idea about what's going on real time, but to predict what should be happen in the future, to predict what if scenarios based on your current situation and get a decision. As you can see on the bottom left of the slide, so this is the transition way for digital twins. Let's start with a digital model, which just a 3D visualization of a physical system or physical model, and then move to the digital shadow, which is a connection between the physical and digital object without any real-time synchronization. It's just an update. And then move to the digital twin, which is a two-way communication between the physical and digital model. So how digital twin work? It simply work as I said, you can imagine that we have a physical world, or like a real world system or object or asset, and a digital world. So once you have your sensors placed in the object, or once you have a data, not about the sensor, once you have the data, you can update your virtual system or virtual model with this real-time data, and update your model, and then with changing, if you need to change the parameters, if you need to change the information, to have a matching between the real world and digital world. And then we can say that this is the digital twin. And then you can continuously learning from the data coming from the sensors, or coming from the information you or like your your sources, to update your model and save your data, or save for your result to be a historical data, and get a decision about your current situation. So that's simply how it works. A little bit about what is the difference between the numerical simulation, or like the traditional simulation, and the digital twin for structural health monitoring. So as you can see here, we are running the model. We are thinking about infrastructure failure, which could be like catastrophic and costly. So traditionally, engineer rely on periodic inspection, or like a fixed sensors, but this is only give like a snapshots in time, not in real time. So it's like, and also it's not near to real time, because once you have the sensors, or once you use the traditional structural health monitoring, you just start by placing the sensor, get the data, and then update your model, and then go back, get the data, and update the model. But this is not like a real time. You can't, if you have any catastrophic failure, or like a serious failure, you can't get it. You can predict it from your model. Also, when something abnormal occur, like a change in vibration mode, or like a sudden temperature gradient, it can raise a flag about this means that we are no longer waiting for cracks to appear. We are detecting changes in behavior that preclude visible damage. However, traditional structural health monitoring still suffer from key limitation, like data scarcity, or like a lack of predictive capability, as I said, which is relying on real-time communication or synchronization between two models. So a little bit about the cases used with digital twins. So as you can see, it's a snippet from different sectors. So we are using digital twin for urban planning, for connecting the infrastructure. We're using digital twin for predicting anomalies or predicting failures in wind turbines. So we are trying to use it for smart cities. We're trying to use it to predict failures, or to simulate the current behavior of the fans, or like what Siemens done with the flight component. They are trying to monitor the real-time behavior of the component while the flight takes place on real time. Okay, so why it's important for structural health monitoring, or why it's important for us as a civil engineer? So as I said, the traditional monitoring can't predict the behavior, can predict the what if scenarios, or the next possible scenario based on the current behavior. So that's why we're trying to think about something smart. We're trying to think how we could integrate or get benefit from other technologies, which is not directly related to civil engineering, in order to advance the way we are trying to monitor the building, with the monitoring the system, predict the behavior of the structures during the operational time, or maybe start thinking how we could use it from the beginning, from the scratch, for all the phases as a civil engineer, like design or construction phases, or any other phases, until we continuously learn over time, and it's after delivery of the project. So now I will be moving to a simple code. So here we are trying. I mean, it was difficult to me to introduce a concept. So what I'm trying to do currently is I try to choose a simple way of using the problem or introducing the problem with the different technologies we were going to introduce in a few minutes. So the main idea here is I pick up like the sine waves, the normal sine wave, and applies these technologies on the sine wave, and how you can have anomaly detection using normal model to detect any points coming from the mathematical model which is not aligning with the normal sine wave, for example. So this is the same concept you can use when you have a numerical data for your bridge, and then once you have a real time data from the sensors, you can start thinking or running the model to see or to try to predict the anomalies. So let me. So far, any questions so far before we start the practical coding? Okay. Right. Can you see the Visual Studio? Anyone? Can you see the Visual Studio?
Yeah, that's clear. Yes.
When I change my screen. Okay. Right. Okay. So for the first code here, I'm trying to show how we expect to get a real time matching between the data coming from the sensors, or the noisy data coming from the sensor, and the digital twin pre-trained on knowledge, or like pre-trained on knowledge from physics, from continuous data. So let's run this code. You can try it. You can have a copy paste for this code on your from the PDF guide, and paste it on the Visual Studio and just run it. So I try to minimize the code as much as I can to do not take much time, but hopefully it's run now. Great. So as you can see, this is what we should expect to get once, if your initial model works fine, you should have a real matching between what you should get from, or what the sensors give you in real time, and your digital twin prediction in case of the real time, or in case of like a healthy state. So once you have a matching between these two data, the digital prediction and your sensor data, that means that your digital model or digital twin model works fine and can predict any deviation, as we will see now. So for the second one here, which we should see, you will gonna see how the model, how the data can be, how the different machine learning models, like isolation forest, which is one of the techniques we use using machine learning. So you have data, train your machine learning model, and then you can, once you have a data which is not matching with your retrained data, you will gonna see that the isolation forest try to exclude the data which is not matching with what has been trained before, or has been seen during the training and validation stage before. So we will gonna see now how the model, once it's trained on the normal sine wave, how the model can predict any anomalies which is not aligning with the normal or the known sine wave. So it's still running. Yeah. So you can see that we're expecting to a normal sine wave will start from 0, but any points which is not or like under 0, or it's not aligning with the normal shape of the sine wave, the model can predict it very easy using the machine learning, a simple machine learning. I'm here speaking about supervised learning. We can think about unsupervised if it depends on the situation, depends on the problem statement. So as you can see here, once we have a data which is not aligned, it's start to be like or not within a range of the sine wave. It start to be in or like detected by the model as an anomaly. Let me do that for another time. Yeah. Okay. Let me back to the presentation. Okay. Right. So now we see the two codes for the digital twin, how should be look like in a simple way, how the anomaly detection work. Now we were gonna start introducing the 3 concepts or the 3 emerging technology which we are aiming to use for advancing the digital twin model. So machine learning is a tool or like a network based on training the data. Like it's coming from the human brain. So you're feeding this machine or like the machine model or the network with a data input, and the model start to be training over the data set and try to understand the difference or like clustering the data if it's unsupervised, or trying to allocate the data between input and output. And then once it's trained, you can be able to use it for any new data to get a prediction or get a classification of damage, for example. So this is a normal way. This is a normal way for machine learning. But what we're trying to achieve now is, what about including what we have learned in civil engineering from physics background into the machine learning network? So how we can include the partial differential equations into the loss function. So this will give you a more efficiency in the predictability of your machine learning. Even if we're introducing a complicity, it will give you at the end a good prediction compared with a normal machine learning. So physics informed machine learning is like a powerful concept. So imagine you are training a neural network to predict beam deflection, for example. So the traditional machine learning would require thousands of labeled data points. But what if you could embed like a physics of a beam, like a physics knowledge of solving a beam using the partial differential equation, or using like the equations for calculating the displacement based on the stiffness and the known load. So that's exactly what the physics informed machine learning does by incorporating the physics law into the loss function of the model. You can reduce the data dependency and ensure that the prediction are physically meaningful, and it's like giving your neural network a scientific compass. So this leads to better generalization, fewer data requirement, and higher trustworthiness, especially important when life and infrastructure are at stake, for example. So a little bit about understanding the physics-informed neural networks. So as you can see in this left photo, so we're trying to have a problem using the physics problem, and then we use the neural network to try to approximate the solution for fastens analysis or fastens prediction during the online monitoring. And at the bottom of this figure, you can see that with using the physics-informed neural network, you can have exactly the same shape as the main problem very quickly during the online monitoring. So it's based on a standard function. So you have a displacement function, which is based on the data and based on the output or input and output, x and t. And then you are trying to use the supervised learning, for example, as it's introduced in the following code here, to learn from the data and try to minimize the difference between the true data and the predicted data, included the physics model here. Also, we are trying to think about how we include the physics law into the model. So like a simple form here, you can have another stock or like a wave equation or heat equation, or as I said, the linear equation we are always using in our linear problem to get the display or to get the displacement or the behavior of the simple beam. And then you can use the physics, as I said, you can use the Navier-Stokes or use the linear equation included into the loss function to reduce the possibility of having a low error or introducing or increasing the possibility of having a low error into the loss function during the training, definitely during the training of the model. And once it's trained, the loss function combine the balance contribution between the data learning and physics contribution. So it's not based on the training of the normal or traditional machine learning. No, we're including the physics insight into the problem on real time. We're trying, I mean, as much as we can to have it near time, because, you know, including physics equations or solving physics equation, particularly if we are looking for nonlinear behavior for those to understand the nonlinear, which is after sometimes with having like a huge amount, a huge load condition or like a very big load, you can see that the material start to behave non-linearly or start to be in damage or like have a bit of failure like concrete. So with including this into the physics into the neural network, it introduced a lot of complication, which we are trying to solve currently to increase the analysis during the online monitoring. Okay, so now let's move to how we use the physics-informed neural network, how it's done in a simple way. So let me share my screen again. So let's run this code, which is based on the physics informed. So you can see once we have trained here, the training loss curve starts lower. So you can train more. You can have more training epoch. You can try to extract a group of data and train on it, and then train again. So you can have a trial and error until you get your desired accuracy. So this is how it works. So how you can have once it's trained, you can see that there's a perfect matching between the true and predicted model for the sine wave. And then you will see in this like a near model how we try to get the true get with using the physics informed neural network, how we can get a true prediction of the correct or sine wave. So here you can see that it's trying to learn with one epoch or like one set of data, but with more set of data, you are gonna get exactly the same as a sine wave. I don't want to waste the time with more running codes for this, but this is how you could use the physics in training the neural network to have a perfect matching where in real time. Definitely, if you introduce a complex problem, like if you apply this on the real bridge, it will be more complicated and take more time to be trained. But the main idea is once trained during the offline stage or during the offline training process, when you move from offline to online, you will be able to quickly assess the behavior of the system. Okay, great. So now I think we can continue here. Right. Okay, Let's go to the generative AI. What is the generative AI and how it it should be used in our case for structural health monitoring, how it should be used in a right way, to have a good data, a good scientific or a good data based on unexpected condition, which a thing we can't currently get from the real applications. So as all of you know, generative AI is like a generative model, a sub branch of the machine learning, more complicated, has a lot of types, as you can see on the right figure. So it's particularly we're going to focus today in the first and second one, the generative adversarial neural network and variational autoencoder, which is something very good for the prediction for the structural health monitoring. And again, we were gonna link the fifth type, which is a diffusion model, but in an advanced way and in a different way rather than the one it's known about. So the main idea is to use the generative AI to simulate these scenarios, whether it's a crack in a bridge, a deck, or like a corrosion in pipeline. We can generate scientific data to train model to classify and predict these damages, which is not in reality, but once we have this data generated or like this scientific data, we could combine it with the normal data coming from the system. And if something of this happened during the online monitoring, you will be able to, as a model, will be able to predict it and give early warning about the possibility of having deviation from the normal state. So the challenge in structural health monitoring, as I said, is the data scarcity. So in the structural health monitoring part of the system, the machine learning model requires large data set, but when we think about failure, it's limited. I mean, the main problem or the main challenge, even to me when I did my PhD, is how to get the data, how to introduce damage to your structure. If it's not damaged, how you can introduce the damage artificially, even if you introduce it artificially in your small scale lab-based structure, you will not be able to have a model which can predict any real behavior, any real failure due to unexpected scenarios or like realistic failure scenarios. So that's the generative artificial intelligence does for us. So it's like linking the gap between creating a realistic failure scenario and learning from the normal state of your structure. So generative adversarial neural network is a type of generative model. So the diagrams show how generative AI fit into the digital twin pipeline. So for generative adversarial neural network, you can simulate anomalies. So you can have a data with a random noise, and then the model will be able to differentiate between training data or like a real data and fake data, and have a discriminator stage which differentiate between real and fake. And at the same time, it will be very helpful if you can see on the left bottom, if you have a bridge deck, you have no damage, you have damage, you can apply you have a variational data, or you have a vibration vibration data, and you can use the GANs to have or differentiate between the data. And then you will train your machine learning or deep learning model. It depends on the complexity of the problem, testing on unknown span of the bridge, which you don't have any data from this, and the model should be learning from the pre-trained data and give you insight about the new data, which is not included in the data set. A simple equations here for a model, or the main idea of how you use the GANs, how we use the concept. So basically here we are trying to use we're trying to minimize and maximize the function with the we're trying to have a probability of the data which is X as a real, and then we can introduce a synthetic data generated from a random noise introduced to the data, so the model can learn to differentiate between different scenarios, between different, let's say, drones images, which is captured from a crack in a bridge column or in a bridge deck. So that's the main idea of GANs. And then if we think about variational autoencoder, which is learning the probability distribution of a failure data and generate a new sample of the data learned from the space. So a simple example here, you can imagine that you introduce a data from a column with one crack in a specific location and a data from the same column with a different location to the crack. The model will learn on this data and combines the behavior, combines this behavior, not just numerical data or not just numerical values. It should be enhanced with images, with other parameters. It could be combined and give the behavior of the column as if these two cracks happen together or appear together in the column. So this data coming from two cracks in a column, it's not introduced at the beginning during the training, but the model learned how to generate data out of the input data, which is not included in the data set. So the main concept here is to have a holistic overview or a holistic data set of what should be possible, what's the possible scenarios, what if scenarios to this column, introducing unexpected scenarios which we couldn't introduce in reality. So once it happened in real life, the model will be able to identify it, will be able to understand from the coming data that it's already trained, and I know this data, so this is relating to this specific damage scenario. Okay, so how it's used in digital twin, as I said, it's like used for creating synthetic failure scenarios to train the machine learning model, to train to increase the efficiency of the digital twin predictability. I'm speaking here about proactive or like predictive maintenance model, not reactive model. And then it improves the anomaly detection. So how can I say it? So imagine that you introduce use the instead of using isolation forest method to have the anomalies predicted deviation from the sine wave, you can introduce variational autoencoder or GANs to learn from the data coming with a possible scenarios of the what data could be identified as a deviation, and you can identify anomalies. It's used in a bridge. It's used in an aircraft structure, as we know. You can understand that it's really important for a lot of parts here. Even if it's not in academia and industry, you can imagine that we are using a monitoring or like monitoring a critical bridge, which is expected to a lot of flooding or a lot of different weather conditions. So the GenAI model will be able to generate a lot of scenarios or a huge amount of data coming from a huge amount of scenarios, which we couldn't have from a real bridge, or wait until it happened in a real bridge to learn from it. So that's why the GenAI could be a bright solution for us to have a holistic overview of data, which be able to predict any unexpected behavior of any physical asset during the live monitoring. So now we will gonna move to how we use GANs, how we use a variational autoencoder on a sine wave generation, how we generate sine wave And then we were going to use the variational autoencoder for a simply supported beam to detect damages in the beam. So we introduce, as you can see here, we introduce a normal parameter, and then we introduce how can I say, like we introduce an artificial displacement, which is a model learn that this is a deviation from the expected displacement or expected behavior, healthy behavior of the beam, and see how the model, how the variational autoencoder system or like model can predict any deviation from the system. So let me share again my VS Code. Right. So this is a simple code for the GANs. So we are trying to use, as you can see, we are trying to use like a signal length. We are trying to use a batch. We are trying to use as 2000 epochs. Here I try to use a lot of, so epochs is you are like 2000 means that you have 2000 trials for each trial or for each epoch. You take a snippet from the data set or like a subset of the data and train the model and see if this data good for the training the model to be able to predict with a higher accuracy. So let's run and see what we were gonna get for this. So you should be able to see the loss function and the normal results from the from the model. So here we're trying to generate, to use a model to generate the data. As you can see, it's try to learning. So we're trying to learn over different epochs, different loss functions, until we get like a good example, a good prediction. I mean, the model should be like a trial and error. So it's, you can see here we have a lot of like an error of 77%. But I mean, you could change your parameters for the machine learning model. You could start having, I mean, in my PhD, and instead of doing this, like not wasting the time, I try to modify the code for the deep learning model or like for the neural network model in the MATLAB to search for the optimal number of neurons, optimal number of epochs, optimal number of layers to be able to get a very accurate decision with a lower loss function. So as you can see here, it start learning, but I mean, it stopped on it's 0.7 loss, which is not completing. But you can also try to do more running code, change the parameters, it changes the epochs, it sends the learning rate. You can, the more increasing the learning rate, the more introduce the complexity to the system and give the system chance to learn more and increase the learning process during the training and validation stage. Okay, let's try the variational autoencoder one. So we're using a Torch, PyTorch library from Python to be able to run the model, to be able to run the generate beam profile for the synthetic data. We use the normal encoder and decoder for the variational model for generating data to be fed to the data set or the pre-trained data for the beam. And then we try to, at the end, try to train the model to over the healthy state of the beam, and then introduce the artificial introduced damage to the beam, and then see how the model will be run. I hope that you can try to copy and paste the code and try it by yourself. Even if you can't do that live, you can try it. After that, you can try to download the guide and work with that. So you can see it's start learning, and then you can see that here we have this damage and we have the with a lot of noise. So once you can use different samples here, you will be able to see that the error is start to be decreased. Okay, right. So far, any questions? I think it's a time for a 5-minute break. If you want to try the codes, if you want to do the code by yourself, or if you want to have any, if you have any questions, just drop it in the question tab here, and then we will gonna continue in 5 minutes. Great, I think we can continue. Is everyone ready? Okay. Right. So the third type of technology we are trying to use for advancing the digital twin for the structural health monitoring purposes as a civil engineers, or like to advancing the traditional way of digital twin, is a dynamic, or is a diffusion model. But I'm calling dynamic because we, as I said before, the main aim is to fasten the real-time synchronization with a higher accuracy. So the snippet shows a lightweight implementation of diffusion based anomaly detector. So the network is trained over a normal structural data like a sensor pattern with no damage. As you can see here, the very basic way is to learn how to identify different animal. This is how it starts. How to differentiate between the numbers. How to learn using the backward and forward propagation methods, and introduce noise to the image pixels, and try to learn from these patterns to differentiate between animals. So it's exactly the same. So when we encounter abnormal inputs in the bridge or in a structure, it struggles to reconstruct them properly. I mean, so the reconstruction error become a signal for anomaly detection. The beauty of this method is basically learn how to differentiate between the anomalies, or between a damage, or between a fake, or like a noise data, because it's trained over the noisy data. So we will visualize how it reacts to the both clean and like corrupted data here. So the main three methods for diffusion model is we are trying to look at, so the denoising diffusion probabilistic model, which is add and remove noise to the generate realistic data useful for image synthetic and the DT protection. We are trying to think about score-based generative model, which uses stochastic diffusion equation, differential equation, which is based on a purely mathematical formulation to refine the data and improve the real-time detection. And the last one is a latent diffusion model, which is operate in a lower dimensional space. So instead, for example, using the dimensionality reduction from the physics space as I used for developing the hybrid digital model during my PhD, we could introduce this into the model, into the machine learning model, to enhance the efficiency and reduce the computational time and fasten the prediction. So here's one of the interesting things by NVIDIA. It's relating to velocity diffusion model. So we are trying, this is important because it could, from the name, it's the velocity diffusion model, which means that we could use it to, during the online monitoring, to enhance the diffusion process and enhance the detection and or like enhance the detector of any deviation from the healthy state image recorded by the drones, for example. So now we will gonna move to a simple regression model using diffusion model to generate the data. So let me code. Right. Okay. So yeah. So I'm trying to show this one here. No, this, I think this should be this one. Yes. Okay. So let's try this one. So this is to learn how the data learn from diffusion process to be able to generate a data which is aligning with the image, or like the way of the sine wave. It's a sine wave. So you can see here it starts learning with a diffusion process, with introducing different noise, introducing different epochs. So you can see that 600 epochs, we introduced 700. So I tried here, because this is the last course, we're trying to introduce different subset of data to try to end up with the same shape of the sine wave. Yeah, so you can see that start learning until we get the correct behavior, or correct like shape of the sine wave. Yeah, So at the end, you will be able to see the green dashed line approximately align with the sine wave. So it starts using the model, the diffusion model or diffusion process concept to introduce or to train the data until we get the same shape of the trained data. And then once it's trained with any other new data, it will be very easy for the model to, which is pre-trained, to identify during the online monitoring. One more thing here is it's a very simple one, but you need to go deeply to understand how it works, how the mathematical formulation to be introduced to the model. But I try to have it easy as much as I can to do not waste the time for running the codes. But you can try, you can feel free to like copy and paste the code and try to play with the parameters, play with the model, with the architecture parameters, learning rate, for example, in the machine learning and so on, to get a better result or to learn how to use this. Definitely for those who don't know how to work with this technology, I know that a lot, or maybe all of us know how to use Python, how to implement codes, but the main idea is how to integrate your knowledge in coding with these new technologies, because it was one of the challenges for me as a civil engineer to learn from scratch how to code, how to programming this coding, how to, for example, use the finite element modeling, how to program, how to use the MATLAB to run finite element modeling without using any software. But the main idea here in this slide is to show you the main softwares we can use, which will make your life easy for generating digital twin, or like having a digital twin model, digital twin dashboard with real-time synchronization between the two systems. So the main, you can use Python, you can use MATLAB, but we can also use ANSYS, which is a finite element software. A lot of mechanical engineer and civil engineer know the software. So you can now they're introducing ANSYS Twin Builder, or like 4 years ago, but with more advanced add-ons over the time. So you can put your component, you can draw your component, you can use a finite element very easy, deploy your sensors, your visual sensor, which is exactly the same location as your physical sensor in the model. Connect these two sensors together, and the model will be real-time updating and doing the finite element very quickly using the dimensionality reduction process or techniques. So that's the main idea here for the ANSYS. But they released 3 years ago a very good video and insightful about the capabilities of the software, how they use the software, how they integrate the emerging technologies to do not only be like a software for finite element modeling or finite element analysis, but be able to emerging the technologies. Now, for example, now they have ANSYS GPT, which you will be able to connect with your agent or the model and say, for example, I have a problem with the software of the sensors. As the model can go and to the programming or to the calibration process and update it or solve the issue. So you can have like a real-time updating for your model without needing to stop your code or to inspect it by yourself. So let's try to open this video.
Has arrived. A virtual representation of a connected physical asset made possible by combining advanced simulation and analytics. Right now, digital twins can predict the future. providing preventive maintenance, optimizing performance, and avoiding product failures. ANSYS Twin Builder makes all this a reality by connecting the power of simulation with real-world operations. Twin Builder offers a complete approach to build, validate, and deploy simulation-based digital twins in the cloud or on edge. First comes build. Twin Builder combines the speed of system-level simulation with the accuracy of physics solvers and allows the reuse of existing components through reduced orbit modeling. ANSYS Twin Builder quickly embeds performance information, cutting run times from weeks to hours. Second is to validate, combining multi-domain systems simulation capabilities with systems validation and optimization. Third, it's time to deploy. Twin Builder creates simpler, highly sophisticated models for real-time deployment. Combining ANSYS simulation and your in-house data yields highly accurate and useful results. The proof and promise of this technology is remarkable. Twin Builder's success in predicting turbine stresses saved a utility more than $100,000 a year avoiding unplanned outages. Twin Builder accurately analyzed the thermal behavior of a manufacturer's motors within milliseconds, not days. Twin Builder speeds the shift to zero carbon by controlling industrial processes, anticipating carbon reduction options, and lowering maintenance costs. The digital twin has arrived in a big way, connecting rapid, reliable system simulations and real-time, real-life operations. Build, validate, and deploy simulation-based digital twins with ANSYS Twin Builder.
Okay, so a quick points for the three introduced software as an example, not in like all softwares, but this is like an example. So MATLAB is an excellent quick prototyping data pre-processing and control oriented simulation. So I have used extensively for reduced space model development in my PhD and use a finite element. So I have a finite element, I have scenarios, apply the reduced space model to trunk the stiffness matrix, for example, to be able to solve the system very quickly. And then with help with machine learning, you can identify which is pre-trained on the data coming from the finite element modeling. You could have a prediction on real time once you have availability of the data from sensors, predict the location, and then go back to the fast analysis to identify the severity of the damage, or like, for example, what's the percentage loss in the stiffness, and what is the crack length, and what's the crack propagation rate on a concrete column. On the other way, ANSYS Twin Builder support real-time, as you saw in the video, co-simulation and connect to the live sensor feed. Python is a backbone of this all AI work and the basic and start way of introducing the AI libraries and code. So each platform has like its own strengths. So I think you can understand more if you start working by yourself with these softwares. You will be able to identify differences, and then you can decide what software to be used. And again, it's linked to the question I raised when I start. What do you want from your digital twin? What do you want to achieve from your model? What do you want to achieve from your digital twin system? Okay, so to wrap up, I think the future is really bright and nice and amazing for us as a civil engineer, for anyone fascinating by these technologies, interested in how you can enhance your ability with these technologies to be integrated in your field or your area of interest. Because 10 years ago back, I would not I wouldn't think that I would be able to use programs or to program my problem using MATLAB or using Python. I was just used to use the normal finite element modeling, not to think about how we could integrate different models. For example, I'm currently looking for self-healing material, which is something interesting, and it should be a core concept of advancing the digital twin. Like to introduce a self-updating digital twin model, self-generating digital twin, which is, for example, we are using the bacterial concrete, particularly Sapulus, which is one of the bacteria. I might be wrong in pronouncing the name of the bacteria, but I'm not familiar with this currently. I'm trying to learn how the codes, how the chemical reactions, how this can be embedded into the concrete. To once we have a crack, you can have this will be interact with this bacteria and water and try to be hardening to filling this crack, and that's it. That is the concept of self-healing material. So a quick roadmap for the next 5 years. So as I said, the future is bright. We are now trying to talk about self-generating or hierarchical digital twin that can build themselves from building information models and design specification. These twins will be able to evolve autonomously and learn continuously from sensor data and be embedded with optimization routines, or like integrating the technologies we discussed during this tutorial, and be and also be connected to the people. We're trying to have a human inside, which is a concept of Internet of Everything, instead of using just Internet of Things to be fit. So the main question is to how the human interaction can be fit to the digital twin model and integrated to be and converted into a real engineering problem to be fit to the digital twin model. So that's simply, we are trying to think about having a hybrid digital twin, which combines the physics-based and the deep learning model, which is something I developed during my PhD, and integrate the technologies like physics-informed models, Gen AI integration, and then we can have at the end a self-autonomous model. And then with the new upcoming technologies with artificial intelligence, you will have more than self-updating model. We will have an autonomous model which could be able to do all of these capabilities and be able to update the physical asset without any human intervention, which is not yet exist, but I think after 5 years from now, it will be something we were gonna discuss, which would be existed. Great. So as a final takeaway, like a few final thoughts. So digital twin are transitioning from static replica to intelligent agent, intelligent system, integrating physics, AI, and real-time sensing, and introduce unprecedented capability to the infrastructure resilience. With tools like physics-informed machine learning or GANs or diffusion model, you will be able to empower your model or your twins to predict, learn, and even act with your physical model. As an engineer or as a researcher or as anyone interested in the technology, you will be able to take place and definitely take place in this cycle. And with your expertise, you will be able to be one of the persons who can introduce the transformation to the systems in your field, not in civil engineering in particular, but in all fields. So that's end from my side, and thank you so much for attending the tutorial. I hope that I cover the main parts of the technologies and relating and linking to the digital twin concept from my field and from other fields. I think we are ready for questions, Yusuf.
Yes, for sure, Shady. Anybody who has a question, guys, you can write it in the question section or in the chat as well. Okay, just a second.
I'm sorry, I can't hear you. There's a lot of background noise.
Okay, is it better now? Okay, perfect. So I was just telling the audience in case they have any questions
Yeah.
regarding this session, they can definitely ask it in the chat or the question section. And I can see that Sophia Sam is asking, will this session be recorded? Yes, the session is going to be recorded, yes. You're most welcome, Sophia. Does anyone else has a question? Okay. No questions so far. Are we good to go? I think this is all for today. Okay, so I'm pretty sure that if anyone had any more questions, they can approach you, Mr. Shadi, anytime. I'm pretty sure you will be open to help, right? Can you hear me? Mr. Shadi, can you hear me? Yeah, perfect. Okay, I just
Yeah, sorry. I'm sorry, the background noise
okay.
is a bit.
I think
Sorry.
right now it should be better. Okay. Okay, I'm sorry for the background noise. I was just saying that in case anybody has a question or something, they can approach you or something. I'm pretty sure that you will be open for help, right?
Maybe we can speak more about the next step for like advancing digital twin, like how we could use self-generating and hierarchical digital twin. So I mean, the main concept of advancing digital twin or let's use this
We really
technology.
apologize for the background.
Can you? I think we have. There's a question. Sorry. Oh no, can you leave your contact info? Probably I can share my screen again and go for the first page, which has my contact. Let me just go back. Yes. Okay. That okay? Can you see the slide? Okay, yeah, good. So as you can see here, it's good to go back to this slide. So for the current focus here, we are trying to advance the hybrid model. So the hybrid model developed during my PhD was a combination, as I said, between the physics-based or the physics knowledge and deep learning. So the main idea is to combine the data coming from the physics-based model, feed it to the data set to the machine learning, without needing to a huge amount or a huge experimental trial or data from experiment or from real application. So we have two things here. Actually, the first thing is reducing the probability of having noise or having a noise coming from the sensor. So the model or the machine learning model can be trained on a good data coming from the numerical simulation, and at the same time using the reduced model or using the reduced space model to fasten the analysis during the online monitoring, give us an idea. Because if you are working during the linear regime, you will be able to have a linear interaction between the snapshots or between the scenarios, which have all of possible scenarios, the healthy state and damaged state, different damage locations, different damage severities. So once you have this interaction or the linear combination of these snapshots, you will be able to come up with a mode shapes. And these mode shapes give you insight on what is the best optimal sensor layout, or what is the best place to put your sensor in the real structure or the physical system. So the main idea here, it was like, for example, instead of putting a normal and random sensors in the physical structure, you will be able to have an optimal sensor layout before even go live, and you can place your sensor based on the prediction from a physics model, which you will be able to, or aiming to get an accurate behavior of the model. And once you feed to your machine, your trained machine learning model, you will be able to, the model will be able to differentiate, because it's trained on the a good data, even with a lot of noisy data coming from the sensor, but with some limitation, definitely, because if you have like a hallucination coming from the sensor, you'll not be able to differentiate between any scenarios. But let's say that we have a filtration process, but after the filtration process, you have like some noises, but still the model can be able to differentiate the behavior between the different scenarios, or the displacement change, the deformation change for different scenarios. So that's the core concept of the hybrid digital twin developed during my PhD study. The limitation, as I said, for this is if you have unexpected scenarios, or if you have because you are training your model on the possible scenarios which should happen in reality, but if you have unexpected scenarios due to change in weather, or you are not expecting to have, for example, a flooding problem, or like a failure due to flooding, because you're not expecting a flood in your area, but the model will not be able to identify it. So that means that the model has restriction. It's a good for real-time prediction. It's a good when you have an insight about the possible scenarios, possible failure scenarios, but it's not suitable when you think about severe conditions, or like catastrophic condition, which you are not be able to get it from the real structure, or wait until it's happened, if it's happened. So that's why we're trying to advance the model to have a self-updating model based on these emerging technologies, or these technologies like GenAI. So you can have synthetic data which is not coming from any numerical or any real data, based on unexpected scenarios introduced to the model. So you can have a huge amount of data, train it or feed it to your model. Once it's happened at any point during your online monitoring, you will be able to identify it, or like have an early warning before it even happened, and have a decision about what should be next. For example, you can have a decision about the best evacuation route during a disaster in a bridge, using this pre-trained synthetic data, or pre-trained huge amount of data based on this scenario, because the model trained on this similar disaster or similar condition. So once it starts to be happen, or like the forecast announced that we are expecting an earthquake, you will be able to have a decision, not training your model because it's trained on similar condition. If you have this, you will be able to identify which is the best route to evacuate from the bridge, which route, and this is definitely cost time, but not preventing collapse of the bridge if it's a big problem. But at least we could have a mitigation. We could have a good insight before it's even happen. Save lives, save money if we manage to avoid the collapse or avoid the problem to increase or to be progressed. So that's the main idea. On the other side, we are thinking about hierarchical digital twin. So in hierarchical digital twin, you are trying. So the problem I introduced now or identified now, it's introduced a lot of complication, a lot of problems due to the computational time, due to the running the models or running the code for real-time simulation. So what we're trying to introduce is a hierarchical system which have a subsystem. So you can have a subsystem digital twin for each component, for each problem. You can have a digital twin for the bridge element or for the structural element. You can have a digital twin for the operational system, for the vehicles, for the transportation, linking all the sectors. Each sector, and instead of linking to a one unified digital twin, could be linked to a subsystem, a sub-digital twin system, which be able to update continuously from based on what's the achieved from the sensors or from this part. And then if it's linked to other subsystems, it will be fed to the other systems. So instead of updating the whole system, you can update the subsystems, which is a little bit fasten the process, not much, but we are hoping to reducing the computational time as much as we can to be able to generate a decision or get a decision very quickly during the online monitoring or during the online or like real life problems or failures or whatever. So that's the main idea for the next step or the next advancement in digital twin. So I think Yusuf, that's all from my side. So probably if anyone has any question raised during this time, I'm happy to answer.
Okay, I think that's all for today, Mr. Shady. Thank you so much for such a very rich session and tech presentation. Thank you so much. You just provided a lot of information. I hope that the audience just got the benefit out of it. And I believe that's all for this session. We still have just one more session to go, so don't go anywhere, guys. We'll be meeting once again for the last session for today. It's going to be 3:15. Until then, I hope you will be having a wonderful break. Goodbye. Goodbye, Mr. Shady.
Thank you so much, Yusuf. Thank you for attending the tutorial.
Mr. Shady.